Hello everyone, and welcome to Rational Science, the only site on the internet that does science and physics. You might say, is that true? Why do you make that claim, that outrageous claim? Well, we're the only ones because everybody else, every single buddy else, does particles and concepts. They move concepts around, and that's irrational. And particles, well, you cannot explain a single phenomenon of Mother Nature's with particles, rationally. So we're different because we have elongated entities. We're saying that all atoms in the universe are physically interconnected. And if you tune in here every week, you'll get an idea of, some of the things that we propose in exchange for what you hear out and see out there. And we have a different site. We also redefine what science is. Science is not the study of anything. You don't study in science. Anybody can study and not understand or be able to explain. No, science is explanation. And we've also created a foundation for the discipline known as physics. Okay, we have defined the words necessary to do physics, to do explanations of physics, physical interpretations, and no one has ever done that in 10,000 years. Okay, and so our site is a little different than all the rest out there. Okay, what are we going to talk about today? Well, we're going to talk a little bit about particles. We've been talking about, for the last couple of weeks, about pseudo-particles and quasi-particles. And today we're going to continue in that line of reasoning, if we can call that reasoning. Here's what we've been doing, just a little summary to bring people up to speed who have not tuned in the last couple of weeks. We've done quasars and pseudo-particles, and what are those? Those are emergent properties. In other words, they're not particles at all. Quantum calls them particles. I don't know why they use the word particle if they're not particles. They're emergent property, and what it is actually is equations that describe collective phenomena, vibrations of many molecules or atoms or electrons or whatever. And so they look at that effect, that phenomenon of the vibration, and they call that whole vibration a particle. And they give them names, like here you have one we talked about the other day, the phonon. Okay. No, it's not like the phone. Hello, hello. No. Phonon is a collective excitation of atoms forming a crystal lattice. Okay, and there you see an example. These are different phonons, the different vibrations. One vibrates that back and forth, the other one front to back and whatever. All these are different kinds of phonons. They call them phonons. Just the whole shebang, the whole vibration that's known as a particle. And it's described mathematically, and they call that equation or that solution, they call that a phonon. Okay, and then they go one step further and they start moving the phonon around. Remember, they can accelerate these things. And before that, we talked about the instanton. And what is the instanton? It's the God particle. It's not the Higgs, which was presented as the God particle. No, this is the real God particle. Why? Because the instanton gave origin to the universe. And it never appeared. It was already there, but even that's wrong to think of it that way. The way it's done, as you can see at the bottom of the instanton, it's got a circle, these circles, okay? And those circles represent space and time. So what happens, and again, this is all from a mathematical point of view. Don't try to visualize, don't try to make sense of it. It's just math, okay? Mathematics, equations, that's all it is. And what they're saying is space and time are wound around it as a circle. And since the circle has no beginning and no end, neither the space and time. That's their logic, if you can call that logic. That's their rationality. Okay, and today we have a special kind of particle. Okay, and it's also a quasi. I call them quasis because they're little quasi, quasis. Okay, and these are known as charge carriers. And you say, what the hell is a charge carrier? Okay, so let's see if I can illustrate this for you. Here's a little illustration of what a charge carrier might look like, okay? So please focus and see if you can understand what a charge carrier is. Okay, here it goes. Those are charge carriers. Little ants going from one place to another, and you can see they're carrying their charges. Little leaves, I guess, okay? And this is more or less the notion of a charge carrier. The problem comes when these people say, well, we have charge carriers that go the other way and have a different charge. Those green ones that you just saw, well, we'll call them negative charges. How's that? So they were carrying negative charges. Now we have them come the other way, and I guess, I don't know, the ants are white, and the leaves are red. I mean, is that what a opposite charge carrier is? Okay, and so here you have them. I guess that's what they're saying. Is that what a charge carrier is? The other one was negative. This guy's a positive charge carrier. And no, you got it wrong. The charge carrier that we're going to talk about today looks more like this. Okay, see if we can get it up there. See there? There is no ant. Okay, and whether there's a leaf, a charge that they're carrying, well, that's up for debate. Okay, but for sure there's no ant. Okay, and so the question is, what do you mean carrier? I thought a carrier was like an ant that carries a leaf, and you can say the leaf is positive. Okay, we'll let it go. We'll call it positive. And the other guy comes in the other direction. We'll call it negative. But here we're talking about charge, which is a concept, first of all. But forget about that. There's no ant. You have the leaf, if anything. If we're going to talk charge, we're going to equate charge with a physical object and say that's what they're carrying. Fine. But there's no ant carrying the leaf. No ant carrying the charge. So what do you mean charge carrier? Okay. And here's a definition of what a charge carrier is, okay, so that you can follow my presentation of their theory. Okay, this is not my theory, by the way. I can only present what they're trying to say in physical terms. Okay, and this is their definition of a charge carrier. Charge carrier, a quasi. It's another one of those quasis. Okay, quasi particle that is free to move, carrying an electric charge. It's going to carry, over its head like the little ants. It's going to carry an electric charge. Okay, especially the particles that carry electric charges in electrical conductors. So, electricity gives you a shock and does little fancy things like turn your light on. They're going to say those are charge carriers. Okay. And okay, what are the examples? Well, the electrons, ions, and holes. Well, an electron, is a little bead. We all understand more or less that. I mean, they always represent it with a little ball, all these balls going across. Okay, so that's a flow of electron beads. We understand the mechanism, okay? Ions, same. That's the atom without the electron. Okay, so those move. Those are positive protons, okay, moving along, okay, usually by some kind of magnetic, mechanism where they're accelerated, usually along a beam line. I've done that kind of work for many years. And then holes. What do they mean? You're going to accelerate a hole? What the hell are you talking about? What is this? So this is the one that I'm interested in, the holes. Okay, what are we accelerating here? It says in a conducting medium, okay, an electric field, whatever that is, we don't know what a field is. Nobody knows. It's just a bunch of numbers around a central point that get weaker and weaker as you go farther away, like gravitational field. It gets weaker farther away from the center of gravity. The electric field, same thing, gets weaker and so on, magnetism. Okay, so electric field is just a bunch of numbers, vectors, that's all it is, magnitude and direction. Can exert force. Well, I don't know, a force, I don't know how you can exert any force with a field, because a field is just a bunch of numbers. And numbers don't usually exert forces. Again, like I said at the beginning, we don't move concepts in physics. Okay, so you got to translate this into physics somehow if you want to give a physical interpretation. Otherwise, to say that a field accelerates or exerts a force, so far you've said nothing. You said love exerts an intelligence. That's all you said. Okay, there's nothing there so far. Nothing to sink my teeth into. Okay, exerts a force on these free particles. Okay, see, now they forget about what a quasi is, what these charge carriers. Now they turn suddenly into particles. Okay, now they're going to talk about particles, and you're going to visualize always some kind of bead that goes through there. Okay, but it's when we get to the holes. That's when we're going to run into a little bit of trouble, because there's going to be no ant carrying its leaf. Okay? So that's the point here. Okay, excessive force on these particles causing a net motion of the particles through the medium. Okay, this is what constitutes an electric current. So when you get a zap, okay, like you touch a live wire, okay, they're saying that's caused by particles, and as we're going to see today, some of those particles are holes. And the holes are the leaf without the ant underneath. Okay. In conducting media, particles serve to carry charge. I don't know how you can carry charge, because, what the hell is charge? And so let's look at a definition of charge so that we can cover that base as well, okay, before we move on. Here's charge, okay, very simple. Electric charge, the property. It's a property, it's not a thing. It's a property, it's like an adjective. It's a qualifier, okay, it's a modifier. A property of matter that causes it to experience a force. Okay, so So here's a piece of matter, whatever you want to think of it, maybe an atom, and this is going to be a property of that particle, and the property is going to experience a force when placed in an electromagnetic field. And there you have a little picture of what they're referring to. And again, they put particles or little beads there, one positive, one negative, and you're going to look at that and say, okay, I know what they're talking about. They're talking about little particles, you know, little grains of sand or dust particles or some little ball, some little bead. And that's not what they're talking about at all. They're going to be talking about fields and properties of fields and forces. They're going to be talking about a lot of stuff that has nothing to do with physics. Okay? We don't have a physical interpretation from any of this. Okay, so just keep that in mind. It's going to be all abstract. Okay? It's all going to be mathematical concepts, which the mathematical physicists, that's what they're called, are going to introduce into physics as if they were objects. I hope you can follow. Okay. Okay, so we've got a charge and a charge carrier. They're carrying charges on the backs of on their backs or over their heads like the little ants there. Okay, here's a typical circuit, okay? And those red little balls, those are supposedly the electron beads. And I haven't drawn the atoms. I just drew the beads. There's a little bit of reason for that. You know, people have forgotten what electricity used to be, which was, you know, electrons going from atom to atom, from valence band to valence band, and you know, just moving along for whatever reason. Okay, they're incited, they're forced to move out by something called a voltage, which is defined as a difference in potential. That's all it is. So far, we have no idea what physical object compels the electron bead to jump from the valence band of one atom to the valence band of another atom. Okay, this is what they're saying is electricity. But okay, we get rid of the atom. We're going to do it with little beads there, the electron beads. And what happens is when you close the circuit, okay, you have a power supply. When you close the circuit, okay, the beads begin to roll around. And since they're alleged to be negative, whatever that means in physical terms, the negative beads go to the positive terminal of the battery or the power supply, whatever you got there. Okay? So, okay, we understand the mechanism. We're understanding what they're saying. They're saying, look, there's these beads. They go around, and we're going to call that electricity. If you put your hand on the live wire, those beads will go right through you and, you know, make you tremble, I guess. You know, I've never touched a live wire myself, so I can't tell you that experience. Okay, why do I make a point of this thing about the electron beads? Well, because, see, classical mechanics used to do it with atoms. What quantum has done, quantum mechanics, has gotten rid of the atom, and it does it exclusively with the electron beads. There is no atom necessary for electrical conduction in quantum mechanics. It's just the flow of beads. They talk about current being the flow of beads of electrons, and so we don't need the atom. They suggest or insinuate that you just have electrons flowing. Okay? Like if you don't need any matter, no atoms in there, all you need is just the electron, if you can call that matter, okay? So it's just the flow of beads. And just for reference, I'm going to compare it against our model, okay, just so you're aware. Okay, this is our model, and that's the torsion of a bunch of atoms which are bound to each other. In other words, they're all merged, and so the whole serpentine, as we call it, spins in situ. Okay, that's electricity. In other words, you cannot do electricity without atoms. That's the point. Okay. That's the point I'm trying to make. And you can see there's different models. You know, you can see the model from classical mechanics has this. It's not even classical because it was a turn of the century, but we can call it classical in the sense that we have an atom at least, and we have an electron. Electron was discovered, or you can say discovered, at the end of the 19th century. So I'm going to refer to that as the classical model, even though it's a quantum model, really. Okay, but the new version is without the atom. And we're saying you can't do electricity without atoms, okay? And our electricity is the spinning in situ of of atoms that are merged one with the other. So it forms this long chain, which we're going to call serpentine, and it spins in situ, okay? And yeah, you know, I've worked with vacuum many years. I can tell you one thing from experience, and you don't have to take my word for it. You can go to any person who works with vacuum, any person, okay? I'm putting my hand in the fire for this. You can go to any person who works with vacuum and electricity inside vacuum chambers, okay? And once you pump it down to -7, -8, -9 torr, and just keep going, at some point, believe me, you will not get any electricity. There will not be any electron beads flowing through that empty space. And you say, why would that be so if now you don't have any resistance? Before you had all these atoms in the way. all this gas that you had in there. Now you remove all that water, all that air, all those gases, that residual gases you might have in there. You might even have back streaming from the pumps or whatever. You can remove everything. You have a perfect vacuum in there. The electrons that go through the circuit now have freedom. You know, the mean free path should have increased exponentially. You have no resistance to the electron flow. You should have electricity flowing there like crazy. And it's the other way around. Once you get into the -7, -8 torr range, there is no electricity flowing. You might have some arcing here and there, I don't know. Arcing is just a little bolt that Zeus sends into your chamber and that's it. But it's not going to be a continuous current. You can't do it. It's simply impossible. So no, electricity is not the flow of electron beads without atoms, which is the quantum version of today, which is what people talk about, and that's what they write. They just talk about the electron flow. They forget about the rest of the atom, okay? And that's where the danger comes in. Now, you need atoms. You can't do electricity without atoms. Sorry. Okay, here's, but we can all understand the flow of electron beads, but that's not what you have. What you have today is also a step on top of that. You need to explain the positive current as well. Okay, and I'll show you why in a minute, okay? But you need to explain the positive current. What do you mean positive current? I thought a current was always negative because it's always electron beads that flow from, the cathode to the anode. It goes to the positive terminal, right? Well, no, this is the version, I'm going to show you in a second here. This is the version of holes, okay? And so what you have is the holes are flowing from left to right, and they go to the negative pole. They go to the cathode. And those are true holes, just absence of electrons. That's what you're staring at. The electrons are allegedly flowing towards the left, towards the positive pole, and when an electron moves from one atom to the one to the left, the hole has moved to the right. In other words, the absence of an electron has moved to the right. They're going to call that absence of an electron, they're going to call that a positive hole. Okay, so we have negative electron beads going to the left, and you have positive holes going to the right. Okay, and yeah, we can get rid of the electron altogether. I guess we can just do this with holes. We can probably even get rid of the atom. Those are silicon atoms, by the way. There's a reason for that. Typically, it's in semiconductors, the business I worked in, where all this is used. Okay, so what they have is silicon. Silicon has 4 electrons in its outer shell. Okay, and with 4 other atoms, silicon atoms nearby, they fill the outer valence band with 8 electrons, so they're satisfied. They don't need anything else. But if you put in there, if you happen to what we call implant, okay, we're going to implant an atom in there that is either phosphorus or boron. If you put boron, what you have is 3 electrons in the outer shell, and so it's missing an electron. And that electron is going to cause electron flows inside that lattice, in other words, that crystal lattice. What you're going to have is electrons from one silicon move to that electron that's missing in the boron. And vice versa. If you put phosphorus in there, phosphorus has 5 electrons in its outer shell, and it's going to be a donor. It's going to donate one of its electrons, which it has no idea what it's going to do with it, and that electron is going to be free to flow in the opposite direction of holes. So we're going to have holes moving in one direction, and we're going to have electron beads, negative electron beads, in the other direction. Holes are positive, electrons are negative. Okay, so this is the notion that we have in semiconductors processing. We have holes and electrons. What is a hole? It's the absence of an electron in a valence band, in the outer shell, okay, of an atom. Okay, very, very scary, because this is what you're staring at here. Okay, you ever see Bugs Bunny? He moves the hole around. And these guys are going to move a hole through the desert. Okay, they're going to move the rabbit hole, so to speak. Okay, very scary stuff. Okay, that's what they're proposing. They're proposing the hole moves. Here's another analogy of what they're talking about. You heard of the puzzle of the 16 squares. Okay, and you move the electron to the right. We're going to call these squares electrons. Okay, and if I got to do this right, I moved it to the left, and I created a hole to the right. And if I move the next one now, let's see if I can do this by looking at, I move that one over there. Where did the hole move? Well, the hole moved to the left again. Okay, and I can continue doing that. Okay, here it is again. I can get it. Okay, and you can see the hole is always moving to the left. And what they're saying is the electron is a little square. And the hole is the hole there. It's the here, the absence of an electron. Okay, so you can see there's a flow of holes, and they're going to call that a current. They're going to say it's like a positive current. Okay, so this is how they're going to do this. Okay, just keep in mind what we're doing here. We're saying that it's the absence of an electron, and as the electron creates an absence of an electron in the previous atom, what filled that is a hole. In other words, what you would be seeing on a screen is electrons going one way and a hole's going the other way. That's the notion. Okay, why do we need this? Well, we need this, for example, in semiconductor processing. You need this because, I took a course, very tough course called device physics. And they go through a lot of calculations. It's just a murder on the math. You got a lot of equations. You have calculus, etc., that you have to apply. And what you're calculating is how many carriers you have to create certain electrical effects. Okay, that's in a nutshell what you're doing. And what are carriers? Well, you have one chunk of matter, silicon, to make it simple. So they have gallium arsenide, they have some other stuff. But let's assume we have silicon. And again, you're going to dope that silicon, in one case with phosphorus, and you're going to have it negatively doped because it's got an extra electron in its outer shell. And the other one you're going to dope with boron, which has it has only 3 electrons in its outer shell. So it's going to be an acceptor type of atom. And so you have this material with phosphorus, donor, negative, and you have this other material with boron, positive. Okay? What happens when you put them together? Well, as soon as you merge them, you create what is known as a depletion zone in between. There's a junction there, and that junction is known as the depletion zone. Why? Because what happens is the electrons get filled in all that region. Okay, so you have neutralized all those atoms at a certain distance from the junction. Okay, and it looks more or less like this. Let's see if I can show you this. Okay, and here you see it. What you have is a p-type region, that's the boron, and you have the n-type region, that's the phosphorus. Okay, as soon as you touch those two pieces, those two chunks of matter, what you create is that depletion region at the bottom. And what is that? Well, you have a negative ion from a filled hole, and you have a positive ion from a removed hole. Okay, so you have this region that is kind of neutralized. Okay, and the only way you can get past that barrier is applying a voltage to the ends. Okay, and at some point you have to have strong enough voltage to create a current to go through that. Okay, that's how they can regulate. How a diode or how an interface in a transistor works. Okay, that's essentially how these things work in general terms. From an electrical point of view, what you have is a little thing that has a little piece of matter. On one side you have phosphorus, and the other one you have boron. Boron is positive, phosphorus is negative. You put them together, you create a depletion zone, and that creates sort of like a barrier. And the only way you can overcome that barrier is by applying a current to the terminals, right? Voltage, and you have current flowing through that depletion region as soon as it's high enough. Okay, as soon as the voltage is high enough. Okay, and you can control that. They have what's called a bipolar transistor, where you control the guy in the center. Okay, also MOS, metal oxide semiconductor, where you control the guy in the center, and by controlling the voltage in the guy in the center, you can control how much flow there is, from right to left, for example. Okay, but that's why they needed to create this whole thing, because they had to explain how you create a depletion region. Okay, the depletion region, all you have is really assuming there are such a thing as electron beads. Well, it gets saturated. That whole region, kind of blends in and turns into this neutral region that you have to overcome with voltage applied to the ends, to the terminals. So we create the hole, and we had to, the quantum mechanics had to invent the hole. And the hole is actually the absence of matter. If you want to consider an electron, a negative electron bead, a piece of matter, well, the hole is an absence of matter. That's what it is. And because the other guy's negative, they put this one as positive. So one question you should ask yourself is whether a positive hole, right, is attracted by a positive proton. I mean, you have this boron atom, you have this phosphorus atom, right? And they have protons in, the planetary atom, which they still use in quantum. They have these protons in the center of the in the nucleus, in the center of the atom. And you have this hole. If the hole is positive, right, because you remove the electron, and that's what a hole is, the absence of an electron, and they call that a positive particle, quasi particle, pseudo particle. Is that pseudo, quasi, attracted, positive pseudo quasi attracted to the positive proton. You have a positive nothing, and you have a positive something in the center of the atom. Okay, is that attracted or repelled? Should be repelled, right? You would think. But you can't repel nothing, and I guess you can't attract nothing either. So maybe it's a meaningless question in quantum mechanics. Okay, so let me give you the notion here. Some people say, well, I'm suggesting that no one understands quantum mechanics. And a lot of people criticize me and say, well, Bill, maybe you don't understand quantum mechanics, but everybody else does. You have people like Feynman, he tells you in your face, look, we don't understand it. Here he is. He says, I think I can safely say that nobody understands quantum mechanics. Do not keep asking yourself if you can possibly avoid it, but how can it be like that? Nobody knows how it can be like that. The more you know how strangely nature behaves under the particle hypothesis, okay, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics, mathematical physics, has given up on that. And you tell them this, you show them this, you say, look, this is Feynman, he's a Nobel Prize, 1965 Nobel Prize in Physics, mathematical physics, mathematics, and he's telling you they don't understand. He said, well, you don't understand what he's saying, you're misinterpreting what he's saying. And he goes through this runaround saying, no, see, he tried to say something else and you didn't follow up on what he was saying. No, he's telling you in your face that you don't understand it, that nobody understands it. Niels Bohr had already said that. Werner Heisenberg, these are the founders of quantum mechanics, they all said the same thing. Nobody understands quantum mechanics. And these people say, no, they do understand, or maybe they're too modest to recognize it, or because how can it possibly be that they don't understand and they invented the bomb, for example, and we have all this technology? Well, again, technology has nothing to do with science. Okay? These are two different aspects of human activity. Developing gadgets, you don't need to understand what a field is. You don't need to understand what light is. You don't need to understand what energy is. You just do stuff in the lab, stuff that you don't see, that you can't touch, and you see certain effects, and you're going to use the effect in some way that is good for mankind. Okay? So you don't need to understand, the fundamentals of what's really going on in that secret world, invisible, intangible world of Mother Nature's. You do not need to understand that, okay, to do technology. So you can invent the bomb without having, without understanding exactly what's going on at the atomic level. And these people explain it with particles, but when you put them against the wall, they say, well, we don't understand it either. And they're telling you that they don't understand it. They tell you over and over that they don't understand it, and the answer is, well, you wouldn't have invented the bomb if you didn't understand it. Okay, so this is a problem. This is a serious problem because people don't understand that. The mathematicians don't understand because they cannot explain in a rational manner what's happening at the atomic level, for example, in the case of an atomic bomb. Okay? And again, the Iranians don't have a bomb. Apparently they don't have a bomb today, and their mathematicians are just as good as the guys in the West. So no, the fact that you know a lot of math and that you can describe and that you know, even if you knew what happens at the atomic level, doesn't mean that you can invent the bomb, because that's done by trial and error. In a lab, you do certain things, and you have to put it together, you have to create a device, and that's got nothing to do with science. Science is about explaining. Tell me what a field is, tell me what energy is, and how it works. That's what you need to do. You got to figure out how the invisible, intangible world of Mother Nature's is. That's what science is about, and that's what we don't have today. Certainly not from quantum mechanics or relativity or string theory, okay? Okay, so here's my summary, my conclusions, okay, and this has to do with overall quantum and in particular the quasi-particles, especially the hole, okay. Here's the summary or the conclusion, okay. A hole is alleged to be a charge carrier, whatever a charge carrier is. What is a charge carrier? It's labeled as a pseudo-particle. Is a charge carrier a particle at all? Why do they use the word particle? Is it to confuse you, to mislead you? So that you think that you're talking about a little bead? Is that the point? To give it some measure of physical interpretation to their abstract equations, to their fields, to their waves, to their pseudo-particles? Is that what it's all about? The term carrier insinuates that a hole is carrying and delivers an object. The little ant with a little leaf. We all understand that. The ant is delivering, it's carrying and delivering a leaf. We all understand that. Okay? We see the movie, we understand it. But to say that a hole is a charge carrier and carries what? Charge over its head? Is that the language that we're seeing here? Is that what the language represents? Okay. So a hole is an empty slot left in the valence band by an electron bead that drifted to another atom. So it leaves a hole behind. They call that hole a something. And they put a little positive sign to distinguish it from the negative electron, which is a bead. So we have a negative bead and a positive nothing. Okay, and the positive nothings flow. That's what a hole is. That's what the quasi pseudo particle is. A nothing that is flowing, that's got charge, positive charge, whatever that is. Holes are alleged to be positive because they travel in a direction opposite to electrons. So the electron is negative because it goes to the left. The other guy has to be positive because it goes to the right. Okay, is that what positive and negative mean? Is that the same thing when we say that a proton is positive? Does it mean it goes to the right while the electron goes to the left? Okay, I mean, if they're positive and negative, you would think that they attract each other, right? I mean, that's the catechism of quantum mechanics. Positive attracts negative. Okay? Depletion layers in diodes and transistors are explained using the hole concept. Okay? So you need to, in fact, if you took like device physics, you get all these gazillions of carriers that you have to calculate, how many carriers you need to put in there to create certain electrical effects. And so these are real in the sense that that's how it's taught. You're taught that you have carriers, hole carriers, they carry charges, and you have to count how many carriers there are, how many ants there are, how many leaves that they're carrying. That's the kind of mathematics you get taught in college. Okay, it's called quantum mechanics. And the physical interpretation of quantum is irrational. And proof of that evidence, you like proof and evidence, demonstration, persuasion, go to Mr. Feynman, he'll tell you, we have no idea what we're doing in a lab. They can describe it mathematically because they see something happening, and they describe the visible stuff mathematically, and they kind of simulate that empty space where they can't see or touch. They simulate that with particles. And that's where they're going to apply their equation to. They say, well, there's so much speed between A and B, so we're going to say that particle took, 5 seconds to get from A to B, for example. And so they're going to assume it's a particle, a one-way particle, and they're just going to describe its motion or its energy or how much force was needed or etc. or how much mass it has. That's the way it's done. Okay? Are there particles? Does that mean there are particles? No, there aren't particles because Mr. Feynman has just told you, and so did Mr. Bohr and Mr. Heisenberg, and they tell you that don't try to visualize this. Don't try to imagine it with particles, but we're going to use the word particle anyways because a particle is just an equation. In the case of quasi-particle, it's more than that. It's just an excitation. You get excited.